All right. Good morning. We are starting the lecture now. I've started recording. Okay. So, right. So we were discussing bridges, and one of the main questions was that if we have a cycle C, well, in a planar embedding, it will be a closed curve. So when can you draw two bridges, both of them inside or both of them outside, in the interior or the exterior, right? So, motivated by that question, let us introduce a little bit of more terminology and then we will be actually proving some things. Okay. So, one last piece of terminology we need is if you take any bridge of a cycle. So, here I have drawn an example. I have a cycle C and a bridge. I want to define the segments of the cycle induced by the bridge. Okay. In Bondi Murthy, just for clarification, they call them segments of the bridge, but I find that slightly misleading or slightly tricky to remember what it means. So I will use a slightly longer term, which is they are segments of the cycle induced by the bridge. Okay. So it's fairly intuitive. Supposing I have three vertices of attachment, U, V, and W, then the segments of the cycle induced by this bridge, it's exactly what you think. There is a green colored path from U to V, which does not contain W. Then there is a blue colored path from V to W that does not contain any other vertex of attachment of this bridge. And then there is, let's say, an orange colored path from U to W that does not contain any other vertex of attachment, right? So these are the three segments of the cycle induced by the bridge B. Okay. If your bridge has exactly two vertices of attachment, U and V, then there will be exactly two segments induced by the bridge. And notice that if there is only one vertex of attachment, then this is not well defined because the segments are supposed to be paths. Okay, so we will require the condition for this definition that the bridge B has at least two vertices of attachment. Okay, and in that case, you will get these segments of the cycle induced by the bridge. And the number of segments will be exactly the number of vertices of attachment. Right? Okay, good. And so why do we need this? Well, we need this for the following. So supposing I have a cycle C. So let's think about it intuitively. Intuitively, when can you draw two bridges, both inside or both outside? So let me put one bridge. Let me put this bridge here. Let's say it has three vertices of attachment. Okay. If I have another bridge, so this is the red colored bridge. Now let's say I have another bridge, blue colored, that is also a bridge of this cycle. Well, in order to draw it inside the same side of the cycle, so let me say this is the interior of the cycle and this is the exterior of the cycle. If I want to put the other bridge in the interior of the cycle, well, then basically it should look something like this. All the vertices of attachment of this bridge should be contained in a single segment of the cycle induced by the other bridge. Okay, and so that's what we are going to define. So in this case, we will say that the two bridges, they avoid each other. Okay, so two bridges avoid each other if all the vertices of attachment of one bridge are contained in a segment of the cycle induced by the other bridge. And in other cases, we will say that the two bridges overlap with each other. So two bridges, B1 and B2, avoid each other if all vertices of attachment of one of them, if you like, you can think of B1, are lie in a single segment of the cycle C induced by the other bridge, say B2. Okay, so in this case, well, you can think of it both ways. Um, Notice that the definition is almost symmetric actually, except when you have one vertex of attachment. So in this case, you can imagine that all vertices of attachment of B2, they belong to a single segment induced by B1. You can also think of it the other way around. All vertices of attachment of B2, B1, they belong to a single segment induced by the bridge B2. That will go up to here, sorry. Okay, so you can interchange them. So long as they both have two vertices of attachment, the definition is actually symmetric. Okay, so is it clear what it means for two bridges to avoid each other? Okay, and if they don't avoid each other, then we will say that they overlap. Otherwise, B1 and B2 overlap. Okay, so intuitively, what we are getting at is when the two bridges avoid each other, you can put them both inside the cycle. You might be able to, assuming some other conditions. You need the bridge to be planar in particular, right? So if you make those assumptions, then it's clear that you need the two bridges to avoid each other if you want to draw them both inside the cycle, right? And what we are going to prove next is that when two bridges overlap, it's precisely because of two possibilities that we discussed yesterday. Either the two bridges are skew or they are equivalent three bridges. So that's our next result. So let's prove it. It's not a difficult proof. So theorem, give me a second. Okay, so this is theorem 10.25 in the text. Overlapping bridges are either skew or else. So when they are not skew, it is precisely because they are equivalent three bridges. That's the only case where the two bridges are not skew. Okay. So is it clear what we are going to try to prove? Right? We are going to assume that the two bridges are overlapping, which means that they don't avoid each other, right? So one of them does not have all of its attachment vertices in a segment of the cycle induced by the other bridge. You cannot think of the two bridges in this way. And that is when they overlap. Okay, so let's prove this. So supposing we have a cycle C and we have two bridges B1 and B2. Observe that if any of them has a single vertex of attachment, then clearly they avoid each other, because that vertex of attachment, it's only one, so it will have to belong to some segment of the cycle induced by the other bridge. Okay, so in this case there is nothing to prove. So if either of B1 and B2 has a single vertex of attachment, are done. Well, then they cannot be overlapping, so that's actually a contradiction. So let's assume B1 and B2 are overlapping. Okay. So now let's suppose that one of them has two vertices of attachment. Suppose one of them has two vertices of attachment. Okay, say B1. Okay, so let's make a quick drawing. So we have the cycle C, and we have a red colored bridge B1, and it has two vertices of attachment. Well, in this case, let's look at the other bridge, blue colored B2. So let me draw it here for convenience. Either all vertices of attachment of B2 are going to be on this path, or they are all going to be on the other path, in which case the two bridges avoid each other. But we know they don't avoid each other, we know they overlap. So that means the only way they can overlap is that B2 has a vertex of attachment which is on this path. It is an internal vertex of this path or of this segment, and another which is an internal vertex of the other segment. And in this case, they are skew bridges, right? So in this case, B1 and B2 are skew. Okay, because they overlap, this must be the situation. Okay, so now we can assume that they both have at least three vertices of attachment, because if one of them has two, then we are done, right? Now suppose that each of B1 and B2 has at least three vertices of attachment. Okay, now either they are equivalent or they are not equivalent, right? Which means either they have the same set of vertices of attachment or they don't have the same set of vertices of attachment. So let's consider the case where they are not equivalent. Case 1, B1 and B2 are not equivalent. So let's make a quick drawing. So let's say B1 has its vertex of attachment, something like this. Okay, let's say there are three. And then we have the bridge B2, right? Now they are not equivalent, which means that you can find a vertex of attachment of B2 which is not the same as the vertices of attachment of B1, or other way around. So you may have to relabel B1 and B2. So one of them could have all its vertices of attachment being a subset of the vertices of attachment of the other one. Okay, but if you relabel B1 and B2, you will be able to find a vertex of attachment of B2 that lies between two vertices of attachment of B1. It lies on one segment. Okay. So think about it. You can always relabel B1 and B2 because they are not equivalent. You can find a vertex of attachment of B2 that lies on a single segment, on a particular segment of the vertices of attachment of B1. Okay. So now, what about the other vertices of attachment of B2? Well, if all the vertices of attachment of B2 lie on this segment, this green colored segment, then they are avoiding each other, which is a contradiction because we know that they are overlapping. So that means there has to be a vertex of attachment of B2 that is not on this segment, which means it has to be somewhere on this segment, on this path. Okay? No matter where it is, I don't care because then I get the skew condition. So now consider the four vertices of attachment that are circled in green. And now you see that B1 and B2 are skew. Okay. So in this case, I'm not writing down the whole argument. It's there in the text. We deduce that, or we argue that B1 and B2 are skew. Okay. So whenever they are not equivalent, this is the idea. You find a vertex of attachment of B2 that lies on a segment of the cycle induced by B1, or you relabel the two bridges and you will be able to find that. And then you find this other vertex of attachment of B2 that is not on the same segment. And now you have these four vertices and they show that the two bridges are skew. Okay. So now the second case is that the two bridges are equivalent. And this case is quite easy. If you have four vertices of attachment of both of them, so let's just take a quick example, although perhaps most of you already see this. If this is your cycle, and let's say you have two bridges with the same set of vertices of attachment, 1, 2, 3, and 4. And let's say you have the blue bridge with the same set of vertices of attachment, 1, 2, 3, and 4. Well, then let's call this B1 and B2. Okay, then what I'll do is I will label them U1, V1, U2, V2 so that I can get the skew condition. Let's see. So I have two vertices of attachment of B1. Let's call them U1 and V1. And I have two attachment vertices of B2. Let's call them U2 and V2. And now U1, U2, V1, V2 appear in that cyclic order. Right? And this is exactly the definition of skew bridges. So in this case, if there are at least four vertices of attachment, then they are skew bridges. The only issue is when they both have exactly three vertices of attachment. And now you don't even have four vertices to locate your skewness. In fact, there is no skewness in this case. It's the same three vertices, and these are equivalent three bridges, but they are not skew bridges. You don't even have four vertices of attachment in total. Okay, so this is it. In the case of 4, you have skew, and in other cases, in the 3 case, by definition, you have equivalent three bridges. Okay, good. So, well, that is it. Right? So this theorem tells you exactly the two possibilities in which your two bridges can be overlapping. Right? And what it really does, it helps in reducing the number of cases. When you have to prove something, you have just two possibilities, either the two bridges are skew or they're equivalent three bridges. Right? Good. Any questions or concerns regarding this theorem? All right. If not, then okay. Okay. So far, everything we have discussed, although I have motivated it by getting a planar embedding of the graph, everything we have discussed so far has been about abstract graphs, right? We have a cycle, we have bridges of a cycle. You don't need a drawing for that, right? Even the definitions of overlapping and avoid bridges avoiding each other, and skewness and equivalent bridges, all of these were completely independent of any planar drawing or planar embedding, right? Good. At no point have we actually used an embedding to prove anything, right? Okay. But now, since our interest is planarity, let's now think of a plane graph and a cycle in the plane graph, which would be a closed curve, and think of bridges with respect to this cycle. Okay, so for the next discussion, G is a plane graph and C is a cycle. Therefore, it will correspond to a closed curve in the embedding, right? And now, because it's a planar embedding, all the bridges of the cycle, if you look at any particular bridge, either it's going to be drawn inside or it's going to be drawn outside, right? Because a bridge is by itself connected, it cannot have some stuff inside and outside by Jordan curve theorem, right? So when we have this setting, we can talk about the bridges being inner bridges and outer bridges, right? So inner bridges are those bridges that are drawn or embedded in the interior of the closed curve C. And likewise, outer bridges are those bridges that are drawn in the exterior of the cycle. Okay, good. And right. And what we will prove is that, well, I don't know if I'll even go to the proof of this. It is fairly intuitive to see why this is true. So the next theorem is that if you look at any two inner bridges, they avoid each other. Likewise, the outer bridges avoid each other. Right? Inner bridges avoid each other, and outer bridges avoid each other. Okay, so in Bondimurti, they actually prove this. Well, this is analogous, so I will put it in brackets. So let's just make a quick drawing and convince ourselves why this should be true without writing a rigorous proof. Okay, supposing so I can use the previous result. Supposing I have two inner bridges that don't avoid each other, which means they are overlapping. By the previous result, either they are skew or they are equivalent three bridges, right? So in fact, that is how the proof proceeds in the text. So if I consider the skew case, supposing I have one bridge B1 that has two vertices of attachment like this, and I have another bridge B2 that has two vertices of attachment. One of them is on this segment and one of them is here. Well, at this point, intuitively, it is clear that you can't draw them both in the interior of C, right? One way to get a rigorous proof is to use the non-planarity of K5 and K3, K33 to do this. I'll give you an example here. So if they are skew, what you could do is you could add a vertex outside, because I will just take this cycle and the two bridges and I will delete the rest of the graph, right? So I'll get a planar embedding of C union B1 union B2. And because they are both drawn inside, they are both inner bridges. Now I can put a vertex in the exterior and join it to all of these four vertices. And notice that now you have a planar embedding of K5 or a subdivision of K5, because inside all of these bridges, you can find paths joining these vertices. So any two vertices can be connected by disjoint paths. These paths are internally disjoint, and that is nothing but a subdivision of K5, right? So the way the proof proceeds is, let's suppose they don't avoid each other, which means they overlap. So then they are skew. In this case, you do the trick I just showed you, and you get a planar embedding of K5. Otherwise, they are overlapping three bridges. They are equivalent three bridges, and which means that they have the same three vertices of attachment. In this case, you will get a planar embedding of K33 by putting a vertex in the outside and joining it to the three vertices of attachment. Okay, so this will give you a planar embedding of K5. And in the other case, which I will just make a quick drawing of. So in the other case, you have the cycle C. You have the two bridges, red and blue. Both have the same three vertices of attachment, and both have been drawn inside, which already seems not possible by the drawing, but we don't need the drawing. It's just for the sake of illustration, right? And now what you would do is you would add a new vertex outside and join it to these three guys. And in this case, your goal is to find a subdivision of K33, of subdivision of K5. And in this case, you get a planar embedding. There are some details you need to work out, how to get a subdivision of K33, but I will leave that to you. Okay, so there is some work to be done to find the subdivision of K33, whereas the K5 one is much easier. And in both cases, you have a contradiction because you have a planar embedding of what we know are already non-planar graphs. Right? So anyways, I don't want to go through the details, but I already gave you the idea behind proving this result. So proceed by contradiction. And use the previous theorem 10.25. Okay. Right. So there is a nice way to visualize this.
Sir?
Yeah, go ahead. Yeah, sorry.
Sir, so are we assuming that adding a new vertex doesn't change the planarity?
Oh, right. Okay. So here is the point. We have a cycle C. We have two bridges that are inner bridges. We are assuming by contradiction that they are overlapping, right? But what do we know? They are both inner bridges. That means that they are both drawn inside the closed curve C, right? So what we are going to do is we are going to take the graph formed by the cycle and the two bridges. We are going to just take this graph, which means you have this closed curve, you have two bridges inside, but there is nothing outside. Therefore, I can put a vertex outside and join it to vertices on the cycle. You agree?
Yes, sir.
Right. So that is the part we are doing. So we are not assuming that you can add an edge, add a vertex, and get a planar graph. We have a planar embedding of the graph. We have a bound. We have the outside face. We are just putting a vertex in the outside face, and we are claiming that that vertex can be joined to vertices on the face without contradicting planarity.
Okay. Yes, sir.
Yeah.
Yes.
Okay, good, good. So we are using the arc-wise connected property of the open set, that is the exterior of the cycle. Okay, good. All right, so this is the plane graph with C as the boundary of the outer face. Okay, and we are adding a vertex on the boundary of the outer face in the exterior, in the outer face. So we are always adding a vertex in the exterior, in the outer face, so we can join it to vertices on the cycle. Okay, good. All right, so far so good. Mm, okay, so we have a few more minutes. I think we might be able to prove something interesting. Let's see. So as far as the terminology is concerned, we are mostly done. Um, most of the concepts related to bridges are done. The next goal, we want to use this theory to prove two results, right? One, we want to prove that a three-connected simple planar graph has a unique planar embedding. So that's our first goal. So the applications of this bridges theory. So the first one, uh-oh, what just happened? Okay. So let's prove the following theorem. Let's see if we have time to finish it today. Every simple three-connected planar graph has a unique planar embedding. Okay, and what that means, just to remind you again, is that any two planar embeddings will have the same face boundaries. Okay, so any two planar embeddings. So of course you can draw them in weird ways, but here when we say unique, we mean combinatorially unique. And what combinatorially unique means is that for any two planar embeddings, the set of boundaries of faces is the same, right? So to give you an example that I probably gave you earlier, is you can take this graph and you can draw it in a way that looks in some sense different, but in reality, it's actually the same drawing. And it is the same drawing in the sense that if you were to label the vertices 1, 2, 3, 4, 5, 6, then the face boundaries will be exactly the same for both drawings. Okay, so if you've got a face with the boundary 1, 2, 4, 5, you've also got a face here with the boundary 1, 2, 4, 5. It's 1, 2, 5, 4. Sorry. Okay, good. So in that sense, these two drawings are the same. Okay, all right. So how does one prove such a result? How can we prove such a result that in any two drawings, the face boundaries are the same? It's not immediately clear how we can prove such a result, right? But I want you to remind you of something. I want to remind you of something else that we proved, which is also has this sort of mystical flavor. A consequence of Euler's formula is that any two planar embeddings have the same number of faces, right? And the way we prove that is just to remind you the number of faces of a graph is the number of edges of the graph minus the number of vertices of the graph plus 2, right? And on the right hand side, these things don't depend on the drawing at all, right? They are completely independent of the embedding. So, so maybe that gives us a clue. We are trying to show that in any two drawings, the faces are the same. How are faces defined? It's completely topological. You need a drawing in order to talk about the faces. But maybe there is a different way of looking at faces in a three connected plane graph that does not depend on the drawing. And if we are able to get a handle on such a equivalent definition, then we will be able to prove such a result. Right? So we need something that is not dependent on the drawings, on the embeddings. Okay. And that brings us to one more definition. Turns out we will define a type of cycle in the graph, and it turns out that these cycles, which are defined independent of the drawing, they are exactly the same as the facial cycles. Okay, so that's the way we are going to proceed. All right, and for that we need bridges again. So let's go back to the definition of a bridge. So remember I explained it by this 3D model using beads and strings and scissors, right? And we defined separating vertices in a similar manner, right? So what was a separating vertex? Just to remind you, when you do this cutting and you get two pieces, so in this case you will get two pieces. You will get one piece like this and you will get another piece like this, right? That is a separating vertex. Otherwise it is not a separating vertex. In the same way, we are going to define a separating cycle and a non-separating cycle. So when you do this cutting business and you get at least two bridges or two pieces, we will say it is a separating cycle. Otherwise, we will say it is not a separating cycle. Okay. So I'm just trying to show you a connection between the two concepts of a separating vertex and a separating cycle, although we don't really care about separating vertices at this point in the course. Good. So a cycle C of a graph G is separating if C has at least two bridges. Otherwise, it is non-separating. Again, I want to point out that the definition we are using is slightly different from what Bondi and Murthy are using. I don't exactly know why they defined the way they did, but in the case of pre-connected simple graphs, so there's an observation I want to point out. In a pre-connected simple graph, um, so the way they define it is they say that a cycle is non-separating if it has no chords and it has a single non-trivial bridge. So if they have just one bridge which is trivial, they don't call the cycle separate non-separating. I'm not sure why. But anyways, I'll just write down the observation. You can prove it yourself. A cycle is non-separating if and only if C has no chords, a cycle C has no chords. So chords means trivial bridges and has precisely one non-trivial bridge, right? So it's almost the same as the definition we are using, but there is a slight difference. And right, so this is the definition of non-separating cycle in the text. I don't see why we need this more complicated definition. I think you can just define it based on the number of bridges. Maybe they have a reason. It might be related to one of their exercises, but then I haven't solved all the exercises, so I don't know. Right? So we're going to use a simpler definition. Either there are at least two bridges, in which case it is separating, otherwise it is non-separating. So non-separating means a single bridge. And I want you to observe this for yourself. Okay, good. And what we will prove in order to prove this theorem is that facial cycles, the cycles that are boundaries of faces in a planar embedding, are exactly the same as non-separating cycles. And observe that the definition of separating or non-separating cycle has nothing to do with the planar embedding. So we have something that is independent of the embedding, and that is what we wanted, right? So the specific theorem we'll be proving is theorem 10.27 in the text. My computer just told me that it wants to restart in 15 minutes. I said, sure. Hashtag Windows. So you have a simple three connected plane graph. And we'll be proving that a cycle C is a facial cycle. So that means it's a boundary of some face. If and only if the cycle C is a non-separating cycle, which means it has exactly one bridge, which kind of makes sense, right? Intuitively, if you have a cycle which is a face, you can't have a bridge inside and outside. So which means that all the bridges are going to be either inside or outside. And because the graph is three connected, it forces the graph to have a single bridge. So this is where we need to use the three connectivity. Because in a two connected graph, clearly you could have a face which has two bridges, one inside, well, both outside, for example, right? And this is a face. But now observe that the graph is not three connected, because if I delete these two vertices, then the graph will disconnect. Right? This is just an abstract drawing, but this is exactly what we'll be proving. That if you have more than two bridges drawn on the outside, then your graph will not be three connected. And so it has to be a non-separating cycle, right? So this is the idea. And what I want you to note is that this part here is not dependent, or it's independent of any embedding, right? So in particular, this tells you that facial cycles are exactly the non-separating cycles, which are defined graph theoretically and not topologically. And therefore, in any two planar embeddings, the non-separating cycles are the same, and these will be the faces of your graph, right? So this implies theorem 10.28. Okay, so we'll complete the proof on Monday, and after this, we will proceed to proving Krotowski's theorem. So I think we should be done with Krotowski's theorem proof in about two lectures. Okay. All right. Any questions or concerns? We still have 2 minutes, but I don't have anything great I want to say in those 2 minutes. Maybe I'll put a corollary of the theorem, which I mentioned earlier, I think, which means that for a simple three-connected planar graph, there is a unique dual. Okay, good. So we'll prove theorem 10.27 on Monday. It will probably not take us too long, and then we will move on to proving Krotowski's theorem. But we won't get there on the same day. We will need at least Monday and Tuesday to finish that. All right. Please let me know if you have any questions or concerns. So I'll stop recording.